what will be the major product? It will be multiple products because you get these molecules. There are many hydrogens there. It's not just one carbon. It's going to be many carbon. Not just two carbon as a propane. It's going to be more than that. So depending on which hydrogen is taken out by the radical, you get to form a different product. The question is, which one is the major product? From here or from there? So let's talk about it. What reagent we are given? Bromine. Bromine and the light. What bromine with the light does? It breaks a bromine molecule into a bromine radical. That's the first, the initiation step. That bromine radical, what it's going to do, it is going to pull out hydrogen from this molecule, and then that's going to create a carbon radical, depending on which hydrogens it pulled out, right? That's the first propagation step. It is a many hydrogens, so we have to talk about one by one. So let's talk about first cases here. This hydrogen is a primary hydrogen, while that carbon just having a one carbon substituents. And these carbons is different from that one, but if you're looking at the degree of substitutions, that can be also called a primary hydrogen because this carbon has just one carbon substituents, same as that one. That carbon has just one carbon substituents. So these are all primary carbon. So that's why I call this hydrogen primary hydrogens. So we have a primary hydrogen there. And then we do have a secondary hydrogens. That carbon having a two carbon substituents. So this is a secondary carbon. So I could call this one secondary hydrogens. And then this one, this carbon has a 1, 2, 3 carbon substituents. So this carbon is a tertiary carbon. So this hydrogen can be called a tertiary hydrogen. And then if you remember that, it takes a different amount of energies to take out the hydrogen from a different carbon with substitution. It takes a more energy to pull out the hydrogen from the primary carbon compared to secondary, compared to tertiary, right? That is kind of all of the stability of the radical we talked about. So let's do one by one. So let's say these hydrogens are pulled out by the bromine. So Fish-Hoek arrow, one electron comes in, one electron of this electron pair comes out, so they make HBr. But the one electrons remaining go to the carbon, that makes this radical. If you decide to go with this one, it's going to have a radical there, you're going to have a radical there, but those are going to be all same primary carbon radical. If you take the bromine, and if your bromine takes out the hydrogen from the secondary carbon, then you're going to get the radical on the secondary carbon. And if the bromine takes out the hydrogen from the tertiary carbon, then you're going to get a tertiary radical. Which of those three will be most likely produce more? The more stable one will be produced more. That's the idea. So is a primary more stable, or the secondary more stable, tertiary more stable? So that's the kind of thinking that we were talking about before. Tertiary radicals are more stable, because I haven't given you the reason yet, but tertiary radicals are more stable than the secondary radical, than the primary radical. Among these three different species, which ones are most likely for more is a tertiary radical. But if you have this one form, this will make the bromine at the one disposition. If that goes through the reactions, bromine is going to go to the secondary carbon right there. If that one goes through the reaction, you got the bromine hang on the tertiary carbon. But because of these things are more stable, that get to form more. And then that means that you're going to have that one produce most amount as a product. So what is a major product of this reaction? It should be this one.
So this is a kind of a thinking that we're going to keep doing it over and over again, the rest of those series. We're going to look at the intermediate, how stable they are, and then more stable forms will probably make a more stable, more abundant products. And then that does not mean that this will never happen, but you will probably get more of this. So you need to be able to compare reactant, products, intermediates by energy level, have to correlate it to their degree of substitutions, whatever. That was a pretty simple, but still like this. The next one, this one will show a little more. So let's talk about this one. The same bromination reaction, you got the bromine with the light, that produces bromine radical forms. And then the same thing, you're gonna have that take out the hydrogen from the molecule. You got carbon, primary carbon, right? Carbon with just one carbon substituents. This one the same as the other one. You get the secondary carbon, that carbon has two carbon substituents. You also have a hydrogen on double bonds. But this is something you must remember. When these radical take out the hydrogen, they don't take the hydrogen from the sp2 carbon. These bonds are much, much more stronger. So these are not the subject of the reactions at all. So do not try to take out the hydrogen from the sp2 carbon. Those bonds are more stronger, so you're not going to be able to take it out. Not these two, those are not the subject of the reactions. Yet there's another one for the tertiary carbon. It's a tertiary carbon, that's a tertiary carbon. So we got primary, we got secondary, we got tertiary carbon. So you can imagine it will produce a three different radical in different positions. Let's say bromine radical pull up the hydrogen from the primary carbon, this one, then you're going to get the radical into this carbon or that carbon, it's the same thing because it's symmetrical. If you get the bromine taking out the hydrogen from the secondary carbon, you got the radical staying in the secondary carbon right there. You got the radical taking out from the tertiary carbon, you got the radical shown there. So this is a primary, that's a secondary, that's a tertiary. We already talked about stability of the radical. Tertiary radical being more stable than secondary. This will be probably most likely form more than secondary, and the secondary radicals are most of the primary. So among those three, which was the most likely form as a high, most abundant amount, this radical, right? But that's not the only reason for these cases. These cases, you see the radical there, and the next carbon having a double bond. What that double bond does to the radical, it makes a resonance structure. It makes a resonance structure. So how to draw the resonance structure with a radical? One electron comes in, one electron, the pi bond comes out, so you get the double bond these positions, and then one electron pi bonds come to that position, so you get the radical there. These two are the resonance structures. So not only being tertiary, these are resonance stabilized tertiary. It's a much, much more stable. So because of that, these will get to form a lot more than the other two. And if that one goes through the same thing, you get the bromination atom to this position. If that one goes to the bromination, you get the bromination atom to there. But resonance stabilized radical. Now this is something that you probably understood expect right now. This radical can go through the reactions, make the bromine comes here. That resonance form also make the bromine comes out and make the bromine goes there. Which one of those two will form? Both. Because if you remember that resonance structures, neither this, neither that, actually meaning that half here, half there. It's not exactly half and half, we can decide. But the thing is that these two both, like let's say 60%, 40%. So both carbon has a radical characteristics there. So each end will go through the reaction. If that one goes through the reaction, you get this. If that one goes through reaction, you get that. So one of the major product in this case is not just one species, it's going to be two products because it's coming out from the resonance stabilized the radical.